Well, hi everybody. We're back again. We're going to continue our work with functions. You're going to notice the format of this video is a little bit different. This is the first one that I've recorded since our governor said that we are all safer at home, and so I don't have the luxury of the equipment at Western that I usually use, so I'm recording these at my house, and so they're a little bit more crude, but I'll do my best to get the information that you need as good as possible. So let's get started. We want to do three main things in this video. First of all, I want you to recognize what a one-to-one function is. Particularly important in this section, we're going to find out what an inverse function is, and then we're going to see how to take a function and its inverse and compose them together. That's going to yield an important result for our work going forward. So first of all, remember the definition of a function is that for every input you get one output. So for example, if I give you the function f of x is equal to 4x plus 3, that's a good example of a function because no matter what number we plug in here, let's suppose we plug in 7. F of 7, well, that's going to be 4 times 7 plus 3, and that means that f of 7 is equal to 31. We had one input and we got exactly one output. So what if something is not a function? Well, for example, suppose we said g of x is equal to plus or minus the square root of x. Then if we plug in a number like 25, then g of 25 would be plus or minus the square root of 25, and that's a problem because that means g of 25 is equal to plus or minus 5. See, we have one input and two outputs. That's no good. If we think about all of our input numbers here, those are the numbers in our domain, and these are our output numbers over here in our range. Then when we plug in the number 25, we get two different outputs. We get 5, and we also get negative 5. So that makes this not a function. So in this example shown, here again, this is an example of an input or domain values and an output value where if we plug 1 as our input value, it corresponds to two different output functions. That is definitely not a function. Okay. Now, a one-to-one function is a function where every input has one output, but here's the key. For every output, there's exactly one input. That means to say every output gets its own input. So let's take a look at two more examples. The one shown in the middle here, this is a function. Every input, 1 or 2, gives an output. That is to say 6, 3 maps to 10, 4 gives an output of 10. But we have a couple of inputs that have to share. Now that's okay, it's still a function, but some functions don't have to share, and we call those one-to-one functions. That is to say, for every number we plug in, we get one number out. Those are examples of one-to-one functions, and those are of particular value. So here, the input of 2 gets its own output, and that output is 9. The input of 3 gets its own output. It doesn't have to share with anybody like it does here. 3 has an output of 10, but so does 4. The input of 4 here has an output of 17, doesn't have to share. This is a one-to-one function. So an informal way of saying this is that inputs do not have to share any outputs. And that's sort of a higher class of function, and that's what we're going to work with for the rest of this topic. Now, you might remember that a function passes the vertical line test. And a quick refresher on that, suppose we have a nice simple function like f of x equals x squared minus 4. We've seen this function before. That's a basic parabola dropped down 4 units. And that's going to look more or less like that. We know that this will be a function because it passes the vertical line test. Anywhere we drop a vertical line, it will only hit that function one time. That means for this given x value, there's only one particular output or y value. And so since this passes the vertical line test, it must be a function. We can take that a little bit further and say that if a function is one-to-one, it'll pass both the vertical and the horizontal line test. This is the first time we've seen the horizontal line test. Why is that? Well, let's look a little bit more at this function that we have right here. F of x is equal to x squared minus 4. Let's choose an input value here, like -3. F of -3 is going to be equal to -3 squared minus 4. Or in other words, f of -3 is equal to, that's 9 minus 4, 5. Okay, that's fine. Our input has one output. Graphically, what that means is if we go back here to -3 on our graph, we would have an output value somewhere up here at 5. But here's the thing. If we plug in 3 into our function, f of 3 turns out to be 3 squared minus 4. Or in other words, f of 3 is equal to 9 minus 4. That's also 5. Now, that doesn't prevent it from being a function, but what it does mean is that -3 is getting sent to 5, and +3 is also getting sent to 5. Our input values, -3 and 3, are sharing an output value of 5. Graphically, what that means is that the point 3, 5 is also on the parabola, but here's the thing. They both have the shared y value. That means that we could draw a line through those 2 points at the line y equals 5, and this fails the horizontal line test. Because it fails the horizontal line test, this must not be a one-to-one function. Well, obviously it's not a one-to-one function because two different inputs, -3 and 3, both shared an output value of 5. If a function passes the horizontal line test, then that means that every input gets its own output. Let's take a look at another function. G of x is equal to x plus 2 cubed. Scoot that up a little bit here. If our function is x plus 2 cubed, you should know what the graph of that looks like approximately. We've seen that before. That's the base function of x cubed, but it's moved. Since that's an inside transformation, that's moved to the left 2. And so that's approximately what that function looks like. Now, if we look at this function, not only would it pass the vertical line test anywhere we drop a vertical line, it would only cross once. You'll notice that here, no matter where we drop a horizontal line, this will only pass once. We shoot a horizontal line there, it only crosses our function once. Horizontal line hits once. Horizontal line hits once. This function passes the horizontal line test, and therefore we can conclude that g of x is a one-to-one function. Okay, here's what I'd like you to do. If you have a graphing calculator, grab it. If you don't have a graphing calculator, I'd like you to use the Desmos app. That's one that I've recommended that you download before. It's free, and go ahead and install that. If you don't want to download the app, you can certainly go to a computer and go to desmos.com, and I'm going to give you a couple of functions to graph. All I want you to do is type these in and tell me whether, based on the graph, these are one-to-one functions or not. So the functions I'd like you to graph are the absolute value of x plus 6 minus 1. The next one I'd like you to graph is f of x is equal to the square root of x plus 4. And the last one I'd like you to graph is f of x is equal to the cube root of x plus 7. Take a minute and graph each of those three on a graphing calculator, on the Desmos app, or at desmos.com, and tell me which of these functions are one-to-one. pause the video and then resume when you're ready to answer those 3 questions. Okay, let's take a look at this first one. There's the graph of the absolute value of x plus 6 minus 1. And if you take a look at that graph, you can see pretty quickly that that would fail the horizontal line test. We could shoot a horizontal line right across here and it would hit the graph in 2 spots. And so this one would fail the horizontal line test, and that means it's not one-to-one. Okay, our second one is f of x is equal to the square root of x plus 4. When you graph that, no surprise, is one of our base functions. You should get the square root function moved to the left 4 spots. Would that pass the horizontal line test? Yeah, any horizontal line that crosses this graph will only hit it one time. This one passes the horizontal line test. It is one-to-one. Our last function, cube root of x plus 7, you can graph that. As you know, that's the same as x to the 1/3 power plus 7. And if you look at this graph, sure enough, that would easily pass the horizontal line test. And so since this one passes the horizontal line test, it is a one-to-one function. Okay, the next thing we need to accomplish in this lesson is to look at what's called an inverse function. Let's take a look at a simple little graphical function here with a domain and range of 4 values each. 1 goes to 8, 3 goes to 4, 4 goes to 10, and so on. Now, because this is a one-to-one function, every single input, like 1, 3, 4, or 7, they all get their own output value, 8, 4, 10, and 2. That means that if we wanted to, we could reverse that function, make the range values the domain values, make these our inputs, and make the function do just the opposite. We could make that function send 8 back onto 1, 4 back onto 3, 10 back onto 4, and 2 back onto 7. That's what an inverse function does. If f is a one-to-one function, which this one on the left is, then the inverse function, and we represent that f with a little -1, what looks like an exponent, but it's not, then that inverse function is also going to be a one-to-one function, but instead of having ordered pairs x, y, it's going to be the y value and then the x value. So another way to say that is this. For this function on the left, we could say that f of 4 is equal to what? Well, based on our picture, f of 4 is equal to 10. We could also say that f of 7 is equal to 2. All right? Well, then it must be true that the inverse function does the opposite. That is to say, f inverse of 10, this will take 10 as the input and send it back onto 4. Or we could say that the inverse function applied to 2, what does it do with 2? It sends it back onto 7. So the inverse function does exactly the opposite of the original function. The original sent 7 to 2, the inverse sends 2 right back to 7. Now we can find inverse functions algebraically using this 3-step process. We'll look at an example here, but what we're going to do is we're going to switch the x and y value. We're going to solve the new equation for y, and then we're just going to rename it as the inverse function. So let's take a look at some examples. Okay, we're going to take a look at 3 examples of functions here and try and find the inverse. Now, we have to note here that we can't find an inverse unless we know the function is one-to-one. We'll see why that is in just a minute. So we have to verify that we have a one-to-one function before we go ahead and find the inverse. If it's not one-to-one, then there is no inverse. We can't even find it. So let's start out with A here. F of x is equal to 7x minus 5. The first question is f of x, which is 7x minus 5, is it one-to-one? Well, how do we answer that? We see if it passes the horizontal line test. So we know about what that is going to look like. 7x minus 5 is a straight line with slope 7 and an intercept of negative 5. So that's going to be fairly steep. It's going to look about like that. The intercept here is 0, negative 5, and our slope is a fairly steep 7, or 7 over 1. So is this line going to pass the horizontal line test? Yes, it certainly will. That'll pass the horizontal line test, and therefore it is 1-to-1. And that means that we should be able to find the inverse. In other words, we can say that the f inverse, the inverse of x, it actually exists. So now let's go ahead and find that. We're just trying to find a function that does the opposite of 7x minus 5. All right, here we go. Step 1. We're going to call this function y equals 7x minus 5. So we're just calling the output value y here instead of f of x. So we're going to switch the x and y value. That means this becomes x equals 7y minus 5. Step 2 is to solve for y. And if we do that, we have x equals 7y minus 5. Let's add 5 to both sides. And we have x plus 5 equals 7y. And we'll divide both sides by 7. And what we end up with is x plus 5 divided by 7. There, we solved for y. In step 3, we're going to replace our y value with the name of the inverse function. And so we can conclude that the inverse function is x plus 5 divided by 7. There it is. We're done. Now we should see if it actually works. Let's see if the inverse function does what it's supposed to do. It's easy enough to check. It's kind of like an airplane. If you get in an airplane in Minneapolis and you fly to Las Vegas, then where should the return flight send you? Well, the return flight should have you get on in Las Vegas and fly you back to Minneapolis. You should end up back where you started. So let's see if this works. Our original function, f of x, was equal to 7x minus 5. Let's pick a number and plug in there. And I'm going to choose 8. Then f of 8 turns out to be 7 times 8 minus 5. Or in other words, f of 8 turns out to be, that's 56 minus 5, 51. In other words, the ordered pair 8, 51 would be on our line. Okay, well then it must be true then that the inverse function should send 51 back to 8. Since f inverse of x is x plus 5 over 7, then f inverse of 51 is equal to 8. So the inverse function sends 51 back to 8. That's exactly what the inverse function should do. It works exactly as it should. Let's take a look at another one. G of x is equal to x cubed plus 2. Okay, is this 1-to-1? Let's find out. Let's picture its graph. The base function here is x cubed. You should know what that looks like. And again, you could use Desmos for this, but part of the goal of this course is for you to be familiar enough with functions to know what that's going to look like. If we add 2 to the end, that's going to move it up 2 units. And so there's our function right there. Would it pass the horizontal line test? Absolutely. Any horizontal line will only hit that function one time, and so it passes the horizontal line test. This is 1-to-1. And since it is 1-to-1, then the inverse function, g inverse of x, must exist. So let's find it. Okay, so let's start with our original function. G of x is equal to x cubed plus 2. We're just going to call that temporarily y is equal to x cubed plus 2. And so we're going to switch x and y. And if we do that, this becomes x equals y cubed plus 2. Step 2 is to solve that for y. So let's take x equals y cubed plus 2 and solve for y. So let's subtract 2 from both sides. Now we're going to take the cube root of both sides. The cube root of x minus 2 is going to be equal to the cube root of y cubed, but that is of course just y, so we can conclude then that y equals the cube root of x minus 2. And then our third step is to simply rename that. And so that's actually the inverse function g inverse of x is equal to the cube root of x minus 2. Now here again, we're done, but let's check it. Make sure that it actually works. Let's pick a number to plug into our original function. Let's take g of 3. G of 3 is equal to 3 cubed plus 2. And therefore g of 3 is equal to 27 plus 2, that's 29. G sends 3 to 29. Then g inverse of 29, we should be able to take our output here and plug it into our inverse function. G inverse of 29 then must be the cube root of 29 minus 2. Or that means g inverse of 29 must be equal to the cube root of 27, but that means that g inverse of 29 is equal to 3. And that's exactly the result we'd hope for. We takes 29 and sends it back to 3 compared to the original function, which did the opposite. Okay, and we have one more here. H of x is equal to 3x squared. So let's first of all determine if that is one-to-one. Well, let's take a look at that. That's going to be a basic parabola, 3x squared. We don't have to know much. All we really have to know is that it's a parabola. And is a parabola going to pass the horizontal line test? No. That function is going to fail the horizontal line test. It's not one-to-one. And therefore, if it's not one-to-one, we have no work to do. There is no inverse function. There is no way to get back and reverse that function. That is to say, the inverse function for h does not exist. And so we're done. There's no work to do. So the key here is, with all three of these functions, we had to determine whether they were one-to-one first. Here, we found an inverse function. Here, we found an inverse function. We did that for both because they were one-to-one. They passed the horizontal line test. That one had no inverse because it did not pass the horizontal line test. Okay, the next thing we want to do is look at the graphs of functions and their inverses. We showed just a minute ago that g of x, which is equal to x cubed plus 2, we showed that its inverse existed. In fact, we showed that g inverse of x turned out to be the cube root of x minus 2. Okay, here we go. Let's start with our original function. G of x is equal to x cubed plus 2. That's a base function moved up 2 units. We know that, but we're going to plot points for this because there's some pretty specific points that I want you to make a note of. So let's pick a few points here. When we let x be 0, this becomes 0 cubed plus 2. We have an output value of 2. We can plot that. When we let x be 1, we get 1 cubed plus 2, or an output value of 3. When we let x be 2, we get 2 cubed, which is 8 plus 2. We get an output value of 10. And so, as we expected, we get this function that zips up to the right. But we can plug in negative values as well. If we plug in -1, we get -1 cubed, which is -1, plus 2 is 1. And if we go back to -2, we get -2 cubed, that's -8, plus 2 is -6. You can verify all those inputs and outputs. You could certainly graph that on your graphing calculator on Desmos as well, but certainly their graph approximately matches ours. Okay, now at the same time we want to graph the inverse function, so let's do that. Okay, so let's take the same idea here. Let's pick a number that we can plug into this function. When we plug in 2, we'll get the cube root of 2 minus 2. That's the cube root of 0, which is 0. And so 2, 0 will be on our inverse function. But wait a minute. This inverse function should be doing the same points that we had here for our original function, except in reverse. Here, 0 as an input gave an output of 2. The inverse function should be doing just the opposite. Let's do one more to verify that. This is an extremely important thing to recognize and understand. These points should be these points in reverse. That's the nature of what an inverse function does. Let's try another one. Let's plug in 3. If we plug in 3, we get 3 minus 2, which is 1. And the cube root of 1 is 1. It works. And so 3, 1 will be a point on our inverse function. All these have to be reversed. 2 to 10 becomes 10, 2. And so 10, 2 will be a point on our graph. Graphically, look at what that means. Up here, from our first function, we said that 2, 10 would be a point on that function. Well, then 10, 2 should be a point on this function, and it is. -1 to 1, that becomes 1, -1. -2 to -6 will become -6 to -2. Now what is that graph going to look like? That's our cube root function moved to the right 2 units by a transformation. And there it is. There's our inverse function. Now the thing I want you to notice here is this. Every point that's on our original function, the x and y value get reversed. 210 becomes 10.2. We had a point here, right there, that was -2, -6. It became -6, -2 on our inverse graph. So look what happened. These two are symmetric. If I turn the paper a little bit, they are mirror images of each other. And they're mirror images over what? They're mirror images over the line y equals x, right down the center of that graph. There's our line of symmetry. Now I'm going to turn that back for a minute and let's talk about that line for a minute. That line is important. This is a line of slope 1 and intercept 0. This is the line y equals x. These are all the points for which the y value and the x value are the same. What happened here will always be true for functions and their inverses. Whenever we find an original function, the inverse will always be the mirror image over the line y equals x. This turns out to be an important function, and we'll come back and talk about that in a minute. But let's look at another one. Okay, I'm going to give you this one for practice. I want you to just make a rough sketch of a Cartesian plane. I want you to graph the function h of x is equal to 1/4 x minus 6. I also want you to find the inverse function and graph that. Hopefully, those two functions will be symmetric over that line y equals x. Go ahead and do that. Unpause the video and then resume to see what that looks like. Let's start by graphing the line h of x equals 1/4 x minus 6. Now, we plotted points for the other one, and we could do that here, but we can also use what we know about straight lines. We have an intercept of -6, and we have a slope of 1/4. So up 1 and over 4, up 1 and over 4, up 1 and over 4, and there's our set of points that will define our straight line. Now, will this function even have an inverse? Let's look at h of x. Certainly h of x would pass the horizontal line test, and therefore, yeah, it's got to have an inverse. So let's find the inverse. H of x is equal to 1/4 x minus 6. We already know it exists, so we can jump into our three-step process. We can say y equals 1/4 x minus 6. So step 1, let's switch the x and y. This becomes x equals 1/4 y minus 6. Step 2, let's solve for y. Okay, we can add 6 to both sides. And now we'll multiply both sides by 4 to cancel off that 1/4. And what we end up with is y equals 4x plus 24. And so we have found our inverse. The inverse of h is going to be 4x plus 24. Let's graph that. Now our graph here isn't big enough to go up to an intercept of 24, but we can still plot a few points and get an idea of what this looks like. But let's be clever about this. Let's look at some of the points on our original graph. On our original graph, 0, -6 was one of our points. That means we should be able to plug -6 into our inverse. And what should it give? Yeah, absolutely, it gives 0. And therefore, that means -6, 0 is a point on the inverse. Okay, here's another one right there. 4, -5 is a point on the original graph. And therefore, we should be able to plug in -5 into the inverse. And if we do that, we get 4 times -5 plus 24. That's -20 plus 24. That's 4. And sure enough, -5, 4 is a point on the inverse. Now we can speed that up a little bit. Here's one more point. 8, -4 was a point on the original, and therefore -4, 8 is a point on our inverse. So there's 3 points. That's enough to see our line. And there's our inverse function, h inverse of x. Now, do they look the way that they should? Well, are they symmetric? Here again, if we turn this paper just a little bit, they should be symmetric about the line y equals x, or a line of slope 1 through the origin. Let's see if that's true. Yeah, it sure is. These two functions, the original function h of x and its inverse, are mirror images of each other over the line y equals x. That's exactly what we'd expect. And so you can really see the graphical relationship between a function and its inverse. All right, now let's take a look at what happens when we compose a function with its inverse, okay? So I'm going to give you a simple function here. F of x is equal to 9x plus 3. Let's evaluate f composed with its inverse. Now, if you don't understand composition or what this little circle means, you should go back and watch the video from Chapter 11, Section 1 to get a better understanding of that. But I'm going to assume you know what composition is here at this point. So we want to compose these two together, but we have to figure out what the inverse function is. Let's do that on a separate sheet of paper. Let's proceed. So first of all, we're going to rewrite that as y equals 9x plus 3. Step 1, we're going to switch x and y. Then this becomes x equals 9y plus 3. Step 2, let's solve for y. Okay, let's subtract 3 from both sides. And this becomes x minus 3 equals 9y. And if we divide by 9, we get y equals x minus 3 over 9. There it is. Step 3 is just to name it accordingly. And so we're not going to call this y anymore, but this is f inverse of x. And it is x minus 3 over 9. And so we get f inverse of x is equal to x minus 3 over 9. All right. Now let's get back to the original task. Now that we know what our function is and we know that f inverse of x is equal to x minus 3 over 9, we can do what we were asked. Okay, so composition says if we want to find f of f inverse of x, remember we should rewrite that right off the bat. We should call that f of f inverse of x. But we know what f inverse is, and so this is the same as saying f of x minus 3 over 9. But then the question becomes, well, what is f of x minus 3 over 9? Well, what does our original function say to do? It says that we should take 9 times our input value, that is to say 9 times x minus 3 over 9, and then add 3 to it. So if we do that, the 9's cancel, and we're left with x minus 3 plus 3. But x minus 3 plus 3 is simply equal to x. And so as it turns out, our original statement, f of f inverse of x, that those two composed functions give us x. Now, is there anything special about that? Yeah, if we started out with x, and then we plug it into our function and its inverse by composition, that is to say one and then the other, we will end up with x. That is always true. In fact, that is one of the most important facts about this lesson. Think about it this way. If you get on the plane in Minneapolis, St. Paul International Airport, and you take the plane and you fly to any destination, it really doesn't matter where you fly to. Once you're there, you should see the sights, enjoy some good food, and then get on the return flight. And when you get on the return flight, where will you end up? You will always end up where you started with. You will end up back at Minneapolis St. Paul International Airport. And so when you compose two functions, you're taking the original function and its inverse, and since the inverse reverses the original, you should always end up back where you start with. Let's summarize that. Okay, very important stuff. We're going to have a upcoming quiz, and I can promise you that this question will be on your quiz. For any one-to-one function of f, if you consider f and its inverse, if you compose f with its inverse or the inverse with f, it doesn't matter what the order is. Usually composition order matters, but it doesn't here. You will always end up with x. And in fact, that function, that idea of starting out with x and ending with x, that's another important idea. We call that the identity function. Usually we call functions f or g or maybe h, but when we name a function I, we're talking about a very specific function. I of x is equal to x. So the identity function simply returns whatever you put into it. So tell me, what is the identity function evaluated at 7? It is 7. Let's do another one. What is the identity function evaluated at -2? I'll let you think about that for a minute. It's -2. One more just to make sure you've got this. What is the identity function evaluated at 317? It's 317. Now, here's what I want you to notice from that. This is exactly like saying our y value equals our x value. In other words, whatever our input is, that's what our output will be. Does that sound familiar? It should, because a minute ago when we were graphing, we saw that these two functions were always symmetric to each other about what dashed line here? The line y equals x. In fact, they are symmetric about the identity function. And this one, we said earlier that they were symmetric. The line of symmetry was the line y equals x. We didn't know it yet, but that has a name. That is the identity function. So, two very important facts here for you to study. And in fact, keep in mind for our final exam, the format is going to be a little bit different, of course, because of our circumstances. But this is something that you should put on a cheat sheet or a study sheet for the final exam. The identity function is given by the line y equals x. And it is always true that if you compose a function with its inverse, you will simply get x, no matter what the original functions are. In fact, let's prove that with an example right here. We want to show that f of x, which is the cube root of x minus 5 plus 1, and f inverse, which is x minus 1 cubed plus 5, we want to show that these are inverses. We're going to do this by plugging one into the other. That is to say, we want to show that f composed with its inverse, we want to show that everything cancels out and leaves us with just x. So let's do that. Okay, here we go. F composed with its inverse of x. That's the same as saying f composed or consisting of its inverse. That'll be f of, well, what is the inverse function? We were told here the inverse function was x minus 1 cubed plus 5. Okay, but what are we going to do with that? That's some complicated notation there. There's quite a bit of parentheses in there. That just tells us that we're going to plug x minus 1 cubed plus 5 into our original function. So we're going to take the cube root of our input value. Our input value x is x minus 1 cubed plus 5. There's our input. Now our function says we should subtract 5 from that and then add 1 to the end. Now let's clean that up. That's the cube root of x minus 1 cubed plus 5 minus 5. Those cancel off. They disappear. But we're still going to have that 1 on the end. But what is the cube root of x minus 1 cubed? The cube root of x minus 1 cubed is just x minus 1, plus we still have that 1 on the end. But x minus 1 plus 1 is x. There it is. It happened again. We just showed that f of its inverse, f composed with its inverse, is equal to x. That means that these are, in fact, inverses of each other. That's only true if they're inverses. As you can see algebraically here, plugging one into the other, they just cancel each other out completely, and we're left with x. Okay, let's just review a couple of key points from this section. The first main point is what a one-to-one function is. One-to-one functions are functions where each input get their very own unique output. They don't have to share with anybody. Some functions share. Some inputs have a common output, and that's okay. They can still be functions. They're just not one-to-one. They're not sort of that higher grade of function. But of course, if one input yields two different outputs, then that's not a function at all. The next thing to know is how we recognize a one-to-one function. We can tell we have a one-to-one function if it passes the horizontal line test. And so we look at any given function, like this one, and if a straight horizontal line only crosses one time, that means it passes the horizontal line test. If it crosses more than once, it fails. Parabola is the best example of a function that fails the horizontal line test. Therefore, it's not one-to-one, which makes sense because you can see two different inputs share a common output with parabolas. Once we know we have a function that's one-to-one, then it will have an inverse, and only if it's one-to-one will it have an inverse. And an inverse function should take whatever the original function does, and it should reverse that. The inputs and outputs of our original become the outputs and inputs on the reversed function. And you can find the inverse of an algebraic function if it's one-to-one by using this three-step process. We started by just calling the function y, we switch x and y, then we solve for y, and after we've done that, we simply rename that new value our inverse function. And you can always check by plugging a number into the original function and getting an output, and then plug that output into the inverse and you should get your original input. But don't waste your time. The first thing you have to do is find if the function is one-to-one. Determine if it passes the horizontal line test. If it does pass the horizontal line test, you will find an inverse function. If it fails the horizontal line test like this parabola would, you will not have an inverse. Next, we saw that if you graph any function, no matter what method you use to graph it, and then you graph its inverse function, they will always look alike. They'll always be mirror images of each other over the line y equals x. And then we saw that that line y equals x is actually important. That's the identity function, the function that doesn't change our input. It just reproduces it as an output value. It's always true that if you plug an inverse function into the original function or plug the original function into its inverse, you will always get complete cancellation of every part of the function and be left with just x. That is always true. And in fact, we use that technique here to take this inverse function and plug it into the original. We showed that everything canceled and we were left with x, and that verifies that they are inverses of each other. Okay, that wraps up this section. We're going to keep working with functions in the next unit, and we're doing all this so that we can build the idea of a logarithm, which is what we're getting close to. So make sure to email me if you have questions. I'm happy to help you out. Otherwise, go ahead and start the next web assign section, and we'll see you again soon.